Good evening and welcome. My name is Ben Tudelo, and I'm an associate professor in the Department of Geoscience and the Faculty of Science at the University of Calgary and the Gallagher Colloquium series lead. It is wonderful to have so many of you joining us online for tonight's Gallagher Colloquium presentation, giving us the opportunity to engage with more attendees from around the world. We are recording today's session and we'll be posting this video on the Faculty of Science website. I encourage you to check our website, science.ucalgary.ca, for event listings and video updates. Tonight, we are connecting with you virtually. I'd like to reflect on who I'm sharing this space with now, both near and far. We are broadcasting from Calgary, which is located on the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, the Piikani, and the Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bears Paw, and Wesley First Nations. The city of Calgary is also home to the Métis Nation of Alberta, Region 3. The University of Calgary is situated on land adjacent to where the Bow River meets the Elbow River, and the traditional Blackfoot name of this place is Mohkinstsis, which we now call the City of Calgary. The Gallagher Colloquium series continues to highlight speakers who share a passion for science, scientific research, and exploration. I'd like to take a moment and recognize the Gallagher family for their generosity and for making this series possible. Their support allows us to promote and build public awareness for science and scientific research and helps us understand why science is fundamental and important not only to our own lives, but to the world around us. I want to remind everyone that we are recording today's session, and I will post the video on the Faculty of Science website. I encourage you to check it out. Now, I'd like to welcome Dr. Dave Eaton from the Department of Geoscience to introduce our guest speaker. Enjoy the presentation.
Thank you, Ben. I am David Eaton, and I'm a professor in the Department of Geoscience and the Faculty of Science. It is my distinct pleasure to be here tonight to introduce Dr. Don White, Senior Geophysicist with the Geological Survey of Canada. Don's career path and my own first intersected nearly 3 decades ago at the GSC in Ottawa, where both of us worked in a seismology and electromagnetism group located at the venerable Dominion Observatory. When I joined the GSC, Don was a newly minted research scientist, having graduated from the University of Toronto with a BSc in physics and UBC with an MSc and PhD in geophysics. At the time, Don was applying his expertise in crustal seismology, serving as scientific lead for Lithoprobe's Trans-Hudson Origin transect located in Saskatchewan. Looking back, it seems that Don must have really enjoyed working in Saskatchewan, because after the Lithoprobe program finished, he then turned to lead the GSC's CO2 storage research programs, first within the Weyburn-Midale field from 2001 to 2011, and then the Aquastore CO2 storage project from 2010 to 2021, both located in Saskatchewan. He also serves as an adjunct professor at École Polytechnique in Montreal and the Ottawa Carleton Geoscience Center. In addition to Don's scientific prowess, he is well known for his insightful and often humorous presentations, and that's one reason he was selected to give the CSEG Distinguished Lecture Tour for 2021-22, which is tonight's presentation as part of that tour. In fact, the last time I saw Don in person was in Ottawa when I was doing the same tour in the winter of 2020, just weeks before the start of the pandemic. Don has experienced an entirely virtual CSEG lecture tour this year, and like the rest of us, I'm sure he's looking forward to more in-person opportunities in the future. Don continues to lead national geophysical initiatives within the GSC, especially focused on carbon capture and storage. So please join me in welcoming tonight's speaker, Dr. Don White.
Well, thanks very much for that introduction, Dave. And I'm just going to bring up my screen here, make sure we've got everything going according to plan. I'm going to hide your lovely faces from the screen. So on behalf of the Canadian Society of Exploration Geophysicists and the Geological Survey of Canada, I'd like to welcome you to the talk tonight. And hopefully you'll learn something new, or perhaps I'll remind you of something you already knew but had forgotten about. So the talk consists of 4 parts. First, we'll talk a little bit about greenhouse gas emissions in the context of climate change. We'll then move on and talk about carbon capture and storage, which is one of the methods we hope will help us reduce emissions to the atmosphere. And then the central part of the talk, the real focus is the Aquastore CO2 project. This is a real project occurring in Saskatchewan today, and I'll focus mainly on the monitoring aspects of the project. And finally, at the end, we'll circle back to the big picture and think about the future of CCS and the role that geophysics has to play in that exercise. So I'd like to start the talk with this animation to remind us why it is that we're even concerned about the storage of carbon. And I'm a simple person. I like to see something, if it's a global effect, I want to see something that's global. And this animation from NASA provides that, showing the minimum sea ice cover in the Arctic over the last 30 years or so, actually 50 years in this picture. And as you can see, over that period of time, as a result of changes to the climate, the ice cover there has been reduced by about 50%. Of course, there is a natural carbon cycle. There's interchange of carbon dioxide from the landmass to the atmosphere and with the oceans. And CO2 that's released from the landmass into the atmosphere has residence times there of decades to centuries. And much of that CO2 ends up in the ocean, which of course affects the chemistry of the oceans. The thing that's changed since the start of the Industrial Revolution is our contribution to that cycle. This comes primarily from the burning of fossil fuels, but other industrial activities like cement or steel production. And in this cartoon, we're actually showing a point source, some sort of factory where we have a flue gas coming out. So this is a localized source of CO2 being emitted to the atmosphere. So it's a prime target for us to actually capture the CO2 locally and do something with it. If we look at global energy consumption over the last 20 years or so, according to energy or fuel type, you can see that during that period of time, no matter which energy type you look at, the demand for fuel or energy has increased over time, and it will continue to do so into the future. On the right-hand side of the plot, you'll see that certainly renewables have increased in their use over that period of time. But by far and away, we are still heavily dependent in a global sense on hydrocarbon fuels for energy. So if we're going to do something about greenhouse gas emissions, we're certainly going to have to address this energy consumption using hydrocarbons. Looking across the world at the CO2 emissions, and you can see who the big emitters are, of course, the ones you would expect, China and the United States. But Canada comes in at about number 11. We can look at that in another way if we do it on a per capita basis. Well, Canada moves up to number 9, and those other large emitters move down the scale. And for the first time, we see Australia on the list in the top 10. So all this to say that Canada makes its fair share of global contributions to the global greenhouse gas emissions, which total for the world are about 36 gigatons annually. Moving on to look at Canada specifically, here we look at greenhouse gas emissions by sector over the last 30 years. And you can see that we've been hovering around 700 million tons emitted since about 2000. It's been pretty steady since then. We haven't really reduced things. The oil and gas sector and the transport sectors together make up about 50% of the total. And of these, the only sector that's really reduced its greenhouse gas emissions over this period of time is the electricity generation sector. And that's really quite important because if we are going to electrify the transport fleet, we need to be using clean electricity to do that. Geographically across the country, we can look at large point source emitters of CO2. The total emitted each year is about 300 million tons from point sources, and that's about 40% of Canada's total. You can see concentrations in Western Canada, primarily in Alberta, associated with oil and gas activities, and then in the industrial corridor that runs from Windsor to Quebec City in Southern Ontario and Quebec. So again, these are ripe targets for capture and storage of CO2. Some everyday examples of CO2 emissions. You and I each year put out about 370 kilograms of CO2 just by breathing. The average household and automobile use contributes a few tons per year. And we know that air transport is quite expensive in terms of greenhouse gas emissions. A flight from Ottawa to Vancouver contributes about 1 ton. So let's move on and talk about carbon capture and storage. As depicted in this cartoon, we have a point source of some kind here, emitting a flue gas that contains CO2. That flue gas is run through a capture plant where the CO2 is captured, separated, and injected into the subsurface for long-term storage. This is an old slide, but the story it tells is still relevant and true. And it shows greenhouse gas emissions, how they're expected to increase over time if we don't do anything about the energy we consume. If we want to bend this curve over and reach targets like net zero at 2050 or whatever the target happens to be, there's no one way of doing this. There's no panacea. In fact, we have to apply a variety of different methods to achieve the goals that we're seeking in terms of greenhouse gas reductions. And carbon capture and storage, people who've looked at this in a serious way, suggest that it should account for about 10 to 15% of the expected global reduction. So that's the kind of target that we're expecting carbon capture and storage to contribute to greenhouse gas emissions, or carbon dioxide in particular, globally. Of course, if we capture it, we need somewhere to store it. And geological formations in the subsurface provide suitable formations for that purpose. Those are listed on the left-hand side of the plot. And in particular, if we're looking at large-scale storage, we need to consider saline aquifers. So these are porous formations that are currently filled with saline brines. This is non-potable water. It's highly, these are highly saline fluids, much saltier than seawater, for instance. On the right-hand side, you can see a list of other geological environments where we might store CO2, but these targets are less further along in consideration or research. About 10 years ago, there was a compilation of storage capacity in North America. And for Canada, I show the plot here. Note on the left-hand side that we're looking at a logarithmic scale. But as noted previously, for large-scale storage, saline formations by far and away have the largest amount of storage capacity. As you can see, if we compare that to the annual greenhouse gas emissions from point sources in Canada, we have, at least in theory, capacities to store that CO2, those CO2 emissions for many years of production to come. You should note that this is theoretical storage capacity, so these are based on static estimates. They're volumetric. They don't take into account pressure fields and dynamics and other aspects of storage, but at least at a first glance, there is plenty of storage. Looking at sedimentary basins across Canada, again, this is from a study put out about 10 years ago. And the basins in red, of course, the Western Canada Basin, including the Williston Basin, and then the Michigan Basin in Southern Ontario, were considered the basins that should be the focus of early studies, primarily because of the geology, but also because of their spatial coincidence with concentrations of point source emitters. There should be significant capacity in Eastern Canada as well on the East Coast, but of course, that hasn't been studied as much to date. So carbon dioxide, like any other gas, has the property that as you compress it, the volume, of course, gets smaller. And with carbon dioxide, there's a critical depth in the earth where the pressures are large enough that CO2 changes from a gaseous phase into a supercritical phase. So if we're talking about efficient storage of CO2, we want to consider formations that are at least 800 meters deep. And by doing that, the volume that would exist at the surface is reduced by several orders of magnitude by the time we inject the CO2 at depth. This is a laboratory produced slide showing what happens when we inject CO2 into a saline formation. So this is a sandstone. You can see the quartz grains here, and the porous space in between the grains is filled by brine. As CO2 is introduced into the pore space, you can see it filling most of the pore, but the mineral surfaces are still water wet. So there's a layer of water surrounding the CO2 in the pore space. And then because there is interaction between the carbon dioxide and the brines, we do sometimes get precipitation of salt. And when we get to the Aquastore project, I'll show you a good example of that and the effects it has. Most of the carbon capture and storage projects in Canada to date have been in Western Canada, from northwest to southeast in northeastern BC, where CO2 is separated in conjunction with gas production. The plan is to store it locally. Moving to the southeast, the Quest project exists north of Edmonton, where Shell has stored about 5 million tons to date in a saline aquifer. The Alberta trunk line is designed to take CO2 captured in the industrial area of Edmonton and transport it elsewhere in the province for storage and other use. The University of Calgary has a research site, as you all know, near Brooks, Alberta. The Weyburn-Midale field has been doing enhanced oil recovery since 2000 using CO2. And for the first 10 years of that, it was a research project looking at CO2 storage. And then the project I'll talk about tonight is the Aquastore project located near Estevan, Saskatchewan. So moving on to the Aquastore project. As noted, it's located in southeasternmost Saskatchewan, just north of the US border. It sits within the Williston Basin. The source of the CO2 is the SAS Power Boundary Dam power plant, where 10 years ago they retrofit one of 4 burners for the purposes of CO2 capture. So the flue gas from that burner is transported over to the CO2 capture plant that was built, where the CO2 is separated. 90% of the CO2 is delivered via pipeline to the Weyburn-Midale field for enhanced oil recovery, and 10% of it comes to us at the Aquastore site, which is located roughly 3 kilometers to the west. That's to the right-hand side of the screen. So to date, SAS Power has captured, or at least late in 2021, they had captured about 4 million tons. This is a depiction of the stratigraphic column, so the sedimentary sequence at the Aquastore site. And protruding to the left are geological units, which are impermeable. These are things like shales and evaporites, which form suitable seals if we're going to inject CO2 into any of these underlying formations. Protruding to the right-hand side, these are porous formations that are suitable for the actual CO2 injection. And at Weyburn-Midale, they are injecting CO2 in the Midale beds at this depth, whereas at Aquastore, we're actually going down to the very base of the stratigraphic column. We're injecting CO2 into the Deadwood and Winnipeg formations that sit directly above the Precambrian basement. So in choosing a site, we knew our source was near Estevan, and we knew we wanted to look at the Deadwood Formation, but we had to be aware of basement highs in the Precambrian surface. So there are places where there is topography on the Precambrian basement where the Deadwood Formation is actually completely cut out. So we wanted to make sure that we didn't drill into one of these basement highs and have no storage reservoir. In terms of the geothermal regime, at the Precambrian basement, we expected to see temperatures exceeding 100 degrees C. And if you've heard of the Deep Geothermal project, it's actually located just to the west of Aquastore, and they're utilizing these hot fluids in an attempt to generate electricity geothermally. As I mentioned, the Deadwood Formation is a saline-filled formation, And it's very saline. In fact, there's more than 300,000 parts per million of total dissolved solids. So as mentioned, this certainly is not potable water. And in fact, this formation is used elsewhere in the province for the disposal of industrial fluids. For instance, the potash mines dispose of fluid within this formation. To get a better understanding of the, and to characterize the reservoir, we compiled a number of logs from wells across the area that pre-existed. And we're looking at about 200 meters here. This is the reservoir formation that we're considering. The Winnipeg Formation is at the top, underlain by the Deadwood Formation. These are gamma logs. So the green patches, the high amplitude gamma response, represent shaly units. And then the low amplitude yellow zones are sandstones, which are suitable for injection. So the well up near Regina is actually quite good. It's got a shale caprock and several intervals of clean sandstones that represent suitable storage reservoirs. However, as we move to the southeast down towards Estevan, especially within the Deadwood Formation, we start to see a lot more shale. So there are good sandstone units, but overall, there is more shale as well. So perhaps the reservoir quality is not quite as good. The last thing we did before drilling was to conduct a 30 square kilometer 3D seismic survey. And of course, that gives you an image of the subsurface stratigraphy. You can see that here, the yellow line represents the injection well that was drilled. And you can see there's nice layer cake geology. The reservoir is down here at about 3,400 meters depth. And then well above that is the prairie evaporite unit. And this is a salt unit. It's about 150 meters thick, and it represents the regional seal. So that if we were to have any CO2 leak from the storage reservoir, we would expect this evaporite to impede any upward flow of CO2 to shallower depths. Just for reference, this is the stratigraphic level where CO2 is injected at Weyburn. Another image from that 3D seismic volume is this one, which shows topography on the Precambrian basement. You can see the basement dips to the south, but also you see the strong north-northwest trending lineaments or topography on the basement, which, as we'll see, has a significant effect on the overlying sedimentary column. Pre-stack seismic inversion was applied to the data from that initial survey. And you can see those same strong north-northwest trends within these porosity maps estimated from the seismic data. So there's reason to believe that these trends will have a significant effect on how the CO2 plume spreads out from the well. If we take a vertical slice through that seismic volume, note the reservoir thickness on the left-hand side, we see the same layer cake geology, but there is a feature here on the western side of the panel where you can see a nice bend in the sedimentary section. This is interpreted as a fault in the underlying Precambrian basement. And within the sedimentary rocks, it could in fact be a subseismic fault. That is a fault with offset that is below the resolution of the seismic data, or it could be some kind of draping of the sedimentary rocks over this topographic feature. We're not certain what it is exactly, but it is a feature that we want to keep track of during monitoring. If it is a fault zone, we want to watch to see if it shows any potential reactivation or even leakage of CO2 from the reservoir. If we move up section, by the time we get to the prairie evaporite, which is this interval, we don't see any strong evidence that that feature extends. So we think it's limited primarily to the deeper part of the section. Looking at that same feature in plan view, it shows up as this strong north-northwest lineament here, offset to the west and continues across the area of interest. So thinking that this could possibly be a fault, we looked at some fault slip analysis. And the good news is that the orientation of that fault, the trajectory of the fault, is basically orthogonal to the maximum horizontal stress direction, meaning that given the injection pressures we're going or are using at Aquastor, we don't expect that this fault, if it is a fault, would necessarily be reactivated. So having characterized the site, we then went in and drilled what was the deepest drill in Saskatchewan, deepest drill hole in Saskatchewan at the time, down to 3,400 meters depth, and it extended about 50 meters into the Precambrian basement. We ran a full suite of logs in both the injection well and then an observation well that was drilled 150 meters away. Those are shown here for the geophysicists in the crowd or geologists. You can have a good look at those. I'm not going to talk too much about them. But note on the left-hand side here, I've identified the various target sand intervals for injection, and the injection well was perforated in 4 of these zones. You can see the perforated zones indicated by these black bars. So there's 1 within the Winnipeg Formation, 2 within the Upper Deadwood Formation, and then a larger interval over the Lower Deadwood Formation and actually extending into the Precambrian basement. At the start of injection, we actually did some flow measurements in the well using a spinner tool, and it indicated that the injection within the Deadwood Formation was split 50-50 between the Upper and Lower Deadwood Formation, and then about 10% of the CO2 was going into the overlying Winnipeg Formation. But as I'll show you later in the talk, this injection profile has certainly changed over time. So at the start of a storage project, if you're considering it, of course, you want to compile as much geological information that you have, use that as the basis for building a geological model, and then using that model to run CO2 flow simulations to predict how the CO2 will spread over time, how large a CO2 plume you'll be required to monitor, and as importantly, if not more importantly, how large the pressure plume associated with injection will be. So this is the initial simple layer cake model that was built for Aquastor. Note that it's vertically exaggerated 25 times. So this is actually a model that's quite flat. So a simulation based on that initial model is shown here. So after the injection of about 100 kilotons of CO2, the model predicts that CO2 will spread out from those perforations symmetrically from the injection well in these nice radially symmetric patterns. But as we'll see from the time-lapse monitoring we've done, that in fact, this is not the case. At the outset, the plan was to monitor the CO2 plume using different geophysical methods. The one I'm going to focus on today is seismic monitoring. And we can, of course, estimate or calculate beforehand, knowing some properties about the rocks. We can calculate what the changes in the geophysical properties of the rocks will be as we replace brine with CO2. So in terms of acoustic impedance, which affects seismic amplitude, we expected to see maximum changes of maybe 10% as CO2 saturation increases. In terms of interval travel times in the reservoir, they're actually very small changes, 1 up to maybe 3 milliseconds. If you consider that we're looking for these changes from the surface, which is 3.5 kilometers up from the reservoir, this is really quite a demanding task. Also note that the modeling predicts, and this is actually an assumption of the modeling, or that comes out of the modeling, and that is that whereas seismic is very sensitive to CO2 being resident within the pore space, once you reach a certain saturation, the response is very flat. So it's less useful for predicting or calculating the actual saturation. So Aquastor being a research project, we were able to go in and try a variety of different monitoring methods. I've grouped them according to the objectives to which they were designed. And in particular, we want to be able to monitor where the plume is. We want to look at any surface deformation or induced seismicity associated with the injection of CO2. We're looking for any leakage of CO2 back to the surface. And then we've made a number of in situ measurements using the observation well that gives us direct access to the reservoir. These are especially useful for calibrating the various geophysical measurements that are made at the surface. So the monitoring methods I'm going to talk about primarily tonight are the time-lapse seismic imaging and then the passive monitoring for induced seismicity. Here we have a bird's eye view of the Aquastor site. The CO2 capture plant is on the right-hand side of the slide. The red line is the pipeline that carries the CO2 to the injection well in the center of this grid. So knowing that we were going to be at the site and monitoring for at least 10 years, and having learned some lessons at the Weyburn project about repeatability for time-lapse surveying, we actually installed a permanent array of 630 geophones. They're deployed at 20 meters depth over a 2.5 by 2.5 kilometer grid. These are short period 10 hertz geophones. And the basic idea here is that if you can bury the geophones, get them through the near surface layer and down below the water table, that each time you go back to repeat the 3D seismic survey, the positioning of the geophones and the coupling should be very repeatable from survey to survey. As well, we use dynamite sources. So the dynamite was drilled into 15 meters depth. And again, that gets us through the near surface layer, which produces the most distortion when you're acquiring seismic data. So this was an important feature for the purpose of time-lapse imaging. CO2 injection at the site began in 2015. And I was told just yesterday, we passed 400,000 tons of CO2 injected. Prior to the start of CO2 injection, we did a baseline 3D survey using the permanent array, and we've been back 4 times since then to record repeat 3D surveys with various amounts of CO2 in the ground. Of course, each time you go back and acquire 3D data, you get a nice 3D cube of the seismic response of the subsurface, which you can then slice and dice to look at whatever geological formation you're interested in. So this slide shows the results of such slices for 4 of the monitor surveys. Labeled along the top is the corresponding amount of CO2 that was in the reservoir at the time. These sections are vertical slices through the cube running from left to right, south to north. Note the reservoir interval annotated on the left-hand side, and the injection well, a log from the injection well, is indicated in the center of each of the panels. So at the time of the first survey, we weren't certain whether we would see any indication of CO2 injection. The array was actually designed for much larger amounts of CO2 injection. So with only 36,000 kilotons in the ground, we didn't know if we'd see anything, but sure enough, we saw amplitude anomalies at the injection well within both the upper and lower Deadwood Formation, but we weren't really convinced these were necessarily real. Also note that as you get toward the edges of these images, you'll start to see more sporadic events, which we believe are simply 4D noise or time-lapse noise. By the time of the second survey, the upper plume continues to grow. The one in the lower Deadwood Formation strengthens in amplitude, and there's some hint of the plume in the upper or in the Winnipeg Formation. At the time of the third survey, for whatever reason, there was more industrial activity in the area, and the seismic data as acquired were about 30% noisier. And you can see the effect that has on the image with all of these spurious events. But if you focus on the injection well, you can see the main plume growing in size. The last survey was acquired in January of 2020. Again, same kind of pattern in the main plume. But for the first time, we see strong evidence for a plume developing in the Winnipeg Formation. And also note that in the lower Deadwood Formation, what we initially thought was a plume really hasn't developed. So either we don't see it or it hasn't developed. Similar slices taken through the observation well show very similar features, but in fact, the amplitude differences there are in fact stronger. At the time of the last survey, we actually went back in and measured flow again. And at that time, there's actually no CO2 going into the lower Deadwood Formation. Almost all of it's going into the upper Deadwood, and still about 10% is going into the overlying Winnipeg Formation. And I'll show you the reason we believe this is the case, that we're not getting CO2 into the lower Deadwood Formation. I'll come back to that later in the talk. We can also look at the development of the main plume in plan view. Note where the injection well is. The circle is radius 500 meters for scale. And the thing you'll note here over the course of these 4 monitor surveys is the plume is not spreading out symmetrically from the injection well as predicted in that first model. But in fact, I've dashed in a line here that indicates that the majority of CO2 is going to the east and north from the injection well. So what could be causing that? Well, let's go back to that characterization survey we did at the beginning. Here's a plan view map of seismic attributes, and here's the flexure feature we interpreted shown here. And superimposed on that are the outlines of the seismically imaged plume as it's grown over time. And you can see that this flexural boundary corresponds quite well with that dashed line I drew based on the time-lapse imaging. So it would appear that this flexure, whatever it actually is presently impeding flow of CO2 to the west from the injection well. We can actually ground truth the seismic images. So the background image here, this orange blob in the upper Deadwood Formation, and then the smaller one in the lower Deadwood Formation, that's the seismic image. We also show logs from the injection well in the observation well. And in the observation well, we acquired a pulse neutron log several times because it is sensitive to the presence of CO2. And at the time of the seismic survey, the only place where the log indicated CO2 had arrived at the observation well, so it had traveled from the injection point 150 meters to the observation well, is where we see the main CO2 plume. In the underlying Deadwood Formation, consistent with the seismic data, there's no evidence in it or the PND log that CO2 has reached the observation well, and similarly for the Winnipeg Formation. So we think that the time-lapse imaging is giving us an accurate portrayal of what's happening in the reservoir. To see whether any of the time-lapse imaging makes general sense, we can do some very simple volumetrics. So here I've taken the area of the main plume imaged seismically as a proxy for the amount of CO2 within that plume, and we can compare that to the known amount of CO2 that has been injected. And at the time of the last survey, the difference was about 20 to 25%. So that is likely due to the fact that there's non-uniform saturation within the main plume itself, and or the thickness of the plume is not constant. As well, we know that at least 10% of CO2 is going into the overlying Winnipeg Formation. So generally speaking, the time-lapse imaging makes sense volumetrically. Of course, another important role of the time-lapse imaging is to continually update the geological model because prediction of where the CO2 plume will go in the long term and how the pressure field will behave are important measurement features. So over time, a number of more sophisticated geological models have been built, and primarily incorporating more of the 3D seismic data, including that flexural baffle, and then also those porosity maps that were seismic based. So in this slide, we can see how the simulations have evolved over time with those more sophisticated models. The original pancake model simulation is shown on the left-hand side, and then the latest model is shown on the right-hand side. The orange pixelated zone on the slides is CO2 saturation predicted from the model. The dark orange corresponds to a pore fluid saturation of about 60% CO2, and the dashed lines are the seismically imaged CO2 plume over time. By the time we include all of the seismic information to date, you can see that the resulting CO2 simulation is a much better to the time-lapse data, and we expect over time this will give us more accurate predictions for future behavior of the reservoir. To emphasize that point, on the right-hand side, here's the result of the original pancake model, injection well in the center, and then with the updated model shown here, where we get a much better match. All right, so let's move on. And we're going to talk about induced seismicity. Whenever you inject fluids into the subsurface, there is the potential for inducing earthquakes, usually of small magnitude, but often or sometimes of magnitudes which are large enough to feel. So this is the historical record of seismicity in southern Saskatchewan. And as you can see, there's very little activity down around Estevan. There are clusters of activity around Esterhazy and Saskatoon. And these are, of course, associated with potash mining activities. So to monitor induced seismicity at the Aquastor site, we actually started about 2 years prior to the start of CO2 injection. We've used a number of different systems, borehole geophones, broadband seismographs at the surface, and then an array of short period, both 3-component and single component geophones. The distribution of those recording systems is shown here. There's a kilometer for scale. The injection well is indicated by the red balloon. SV1 through 5 are the broadband seismographs, all located within a few kilometers of the injection well. And then the short period geophones are shown in the cross pattern here. Those have all been recording continuously since the start of injection. Here's the record of measured seismicity over the last 6.5 to 7 years. And you can see the only thing that has been recorded are activities, again, associated with potash mining, and then a few events down here in Montana. You might ask the question, well, perhaps our recording system isn't working properly. Well, we regularly record local mine blasts from coal mining operations, and as well as teleseismic events are identified each month. So we have a well-calibrated system and know it's working well. So we can summarize that by saying that over the last 6.5 years, now almost 7 years, we haven't seen any evidence for induced seismicity. And we think we would see magnitudes down to at least magnitude 0 and maybe as low as -1 using the surface detection system. If we compare that to the Shell Quest project, who are injecting actually into the same basal Cambrian sandstone, but of course, hundreds or maybe even 1,000 kilometers away, they've seen a fair bit of induced seismicity. Of course, these are all very small events, magnitudes less than 1. They occur almost exclusively in the Precambrian basement, but of course, they're injecting at much higher rates and have an order of magnitude more CO2 in the ground over the same injection period as compared to Aquastor. All right, so to wrap up the talk, I want to return to the large picture. And this is a map of carbon capture projects around the world. This is in 2020, so it's relatively recent. And there's a total of about 40 million tons per year being captured. You recall at the start of the talk, we talked about the goal for CCS, somewhere between 10 and 15% of CO2 reduction. What that will require is about 120 gigatons of cumulative CO2 reduction by 2050. That will require at least 5 gigatons per year from CCS. So if we compare what we're currently capturing, roughly around 40 million tons per year, global efforts are going to have to be scaled up by 2 orders of magnitude to meet these kinds of goals if we're going to do this with CCS. So clearly, this is a huge task in front of us. There was a recent paper published in Nature by Ringrose and Meckel, where they looked at the feasibility of this ridiculously large task. And they concluded that it could be done with a total of 2,000 injection sites. They focused on offshore sites, but that would include about 20,000 injection wells. And it would be the equivalent effort of developing 2 Gulf of Mexico or 2 North Sea oil fields from scratch. The good news, I guess, in this story, and looking ahead to how we're going to achieve this, if it's going to happen, and that is that the oil and gas sector has been doing this sort of thing for at least 40 years. CO2 injection has occurred in the Permian Basin since the 1980s. So the expertise certainly exists and will and should be exploited for this purpose. Just to give you a better idea of that task, so this is the southern coast of the US and the Gulf of Mexico. We're looking at about 1,000 kilometers of shoreline here. And since 1942, there's been about 6,000 installations as shown on this map, of which there are about 2,000 that are currently active. So this is a huge task in front of us. What will the role of geophysics be? Well, I mentioned early on that in terms of storage capacity estimates, to date, they're theoretical. So there's a lot of work to be done in actually proving up resources and reserves in terms of storage. In terms of storage, site selection and characterization, geophysics will have a role to play, but I think the biggest role it will play will actually be in monitoring these sites in all aspects of that. And this isn't a short-term endeavor. Monitoring will have to go on for the period of operation of these sites, so that will be decades, almost certainly. And it will also continue for some period after these sites are shut down. So we're near the end of the talk. I just want to acknowledge people who've contributed to the research. There are a lot of people. I haven't listed them all, but these are some of the main contributors, and as well as funders of the research that has been done in the project. So to end the talk, I'm going to show you two movies. And the first one is a technical one. And we talked about salt precipitation. And we also talked about the fact that whereas at the start of injection, we were getting significant injectivity within the lower Deadwood Formation, but over time, there's next to none, as evidence both from the PND logs, but also from the time-lapse imaging. So to find out what was going on, we put a camera down the well. So this is a shot from a camera that's sitting in a column of supercritical CO2. We're looking at the well casing, and these circular holes in the well casing, those are the perforations that allow the CO2 to flow into the formation. So this image is from the upper Deadwood Formation. We're at 3,300 meters depth, and the temperature there is 93 degrees C. So let's move down, and you can see some flakes. This is salt sloughing off the edge of the casing, knocked off by the camera, and you can see that these perforations are still perfectly clear. But then once we jump down to the lower part, we're now into the lower Deadwood Formation. There's a lot more salt being knocked off the edge by the camera. And the perforations you can see are entirely clogged with salt. As we move down further, you can see similar thing. Salt is totally clogging up the perforations. And then as we keep moving down the borehole, eventually we get to the point where there's so much salt built up on the casing of the well that the camera can go no further. So you can see that obviously there are some operational issues, although we talk about this as more in theoretical terms. When we actually go to do this, there are practical issues that need to be considered in real carbon storage projects. So the last movie I'll show you is really more just for fun. If you've never seen what compressed CO2 looks like, here's what it looks like. And with that, I'll thank you for your attention, and I would be happy to try and answer any questions you might have. Thank you.
Thank you very much, Don, for sharing your research with us this evening. That was fascinating, and I also really enjoyed the visuals there at the end. I know that many of you out there in the audience will have questions for our speaker. Please type them into the Q&A box at the bottom of your screen. We appreciate all your questions, but of course, due to time, we may not be able to answer all of them. We'll do our best to get through as many of them as we can tonight. I will group similar questions together as necessary in order to get through the most questions as possible. I was extraordinarily excited, Don, to hear about your imaging of the basement topography in the Estevan regions of Saskatchewan. Just a little bit of context, I've been working with DEEP and the GSC to do some exploration of the geothermal capacity, not of the Deadwood, but of the lower Precambrian basement rocks. And it was interesting to see all of these structures that you were able to pick out in the geophysical data. I mean, is that type of stuff that you see in that data, is that sort of an understanding of the tectonic history of the basin? And do you have any idea sort of how that affects perhaps leakage or transport of the CO2 or fluids into those deeper Precambrian basement rocks based on the geophysical data?
Yeah. So that's a good question. And so those images, so that interpreted Precambrian fault, of course, that does, depending on whether that's a sealed fault or what kind of permeability it might have, that certainly represents a potential conduit for the transfer of CO2, but perhaps more importantly, pressure communication into the Precambrian basement. If you've been following the story of that Mark Zoback tells of the Precambrian crust being critically stressed, a feature like that would certainly be of concern. And generally speaking, in the last 10 years, it has the common wisdom based on experience now is that with these basal units, ideally you'd like to have some sort of sealing unit to keep pressure communication from those basement rocks. So in hindsight, perhaps we should not have drilled into the Precambrian basement, but this being a research project that started over 10 years ago, that's what we did. So it's actually an interesting experiment. So we do have this structure. As we pressure things up, will we see anything? We haven't seen anything to date, but we will continue to monitor over time.
Thank you. That's very fascinating. And I will follow up on that, I'm sure, at some point. So a question from Thomas Gallagher, one of the namesakes of this lecture series. Can you speculate about the economics of CCS, cost of separation and injection, and the rate of injection versus, I guess, the overall economics of the project?
Yeah, so I'll give you some round numbers. This certainly isn't my area of expertise, but I've been involved in this community for quite a long time, and at least I'd say 10 years ago when they were looking at carbon capture and storage, capture has been the most expensive component. And back in the day, the numbers that were put out there that, if you had an operating plant, eventually you might capture CO2 at about $100 a ton. The storage and monitoring costs that would be associated with that would be somewhere more like $5 or $10. So a very small amount relative to the overall amount. And think back at prices on carbon, until recently, they've been sub $20. So it wasn't a very good economic proposal if you pay $100 to capture it, and it's only worth $10 to $15 or $20 to store it. But that has changed. I don't know what the current numbers are, but I have heard numbers. They have come down for capture. I've heard numbers more like $40 to $50 a ton. But that's about as much as I can tell you about that.
Thank you very much for that. I think in my own work, I think that's the biggest number is always on the capture, right? And so I think it's hard to get around that, but also that's where the innovation lies. So if you can figure out how to capture it more efficiently, I think there's lots to be done there. So a question from Paul Baumann, who is one of our previous Gallagher lecturers. How much CO2 is produced in creating the energy to inject the CO2 versus what the net amount of CO2 injected is versus the total? So I think this is similar to the last question over the overall budget here of CO2.
Right. Sorry, can you repeat the first part slowly?
Yeah, how much sorry, I know I talk way too fast. How much CO2 is produced in creating the energy to inject the CO2? So like you're essentially you have to be net increasing the amount of CO2 produced by capturing it.
That's right. So there is a parasitic load associated with CO2 capture. And once you capture the CO2, then you have to compress it to deliver and inject it. I don't know. I can't give you an accurate number, but the number, and it will depend from different capture plant to different capture plant, but the number I have in my head, it's about 15% extra. So, you know, let's say 10 to 20%. It's something like that. It's not 1%.
It's better than it was about 20 years ago. I think it was like 100% 20 years ago. So we're getting better, I think, or it was higher at least. So
Yeah.
Another question from an attendee, Howard Brown. Are CO2 sequestration efforts focused on ambient or site-specific sources such as power plants, or are there other places where you would focus these efforts? I think the Estevan situation is the Boundary Dam project, and I guess that's probably pretty standard.
Right. So there are going to be some plants where they produce enough CO2 and where storage locally is perfectly feasible. And I think those are sort of the easiest cases. I think when you get to smaller point sources of CO2, so if you have smaller plants that are geographically distributed, how then do you capture that CO2 and get it to a more central storage location? So people are looking at this, how best to match the geographic distribution of point sources with suitable storage locations. So that certainly is an important part of the process. I don't know if that answers your question. It's not just power production. There certainly are other kinds of plants. You know, people say, well, if we stop using hydrocarbons, we don't need to worry about carbon capture and storage. Well, of course, there are other industrial activities like cement production, steel refineries, where CO2 is a byproduct that needs to be taken care of if we're going to continue that kind of production using current methods.
Totally. And I think that was a good answer to that question. I think Alberta has been focusing on the carbon trunk line, right, to sort of feed those smaller sources into the bigger injection operations. So another question here from Dr. E.F. Malone about the Western Canadian sandstone layers and sort of what's there versus what you're going to put into there. So you are obviously, or all of us are proposing to inject CO2 into these, but what is there currently? So he proposes, or they propose to have brine, and that there is brine in these aquifers, but what else is there?
What does the brine consist of? Or
yeah, what is the brine? Are there also other things like hydrocarbons that are in these reservoirs? What are you going to be displacing by injecting CO2 into these reservoirs?
As far as I know, I mean, if we want to restrict it to the Deadwood Formation, I don't think there's a lot of hydrocarbon production, for instance, from the Deadwood. There may be some, but it's not a big producer. I'm pretty certain of that. Yeah, so I guess the main thing, you know, that is a concern is brine displacement and the pressure field associated with injection activities. And that really comes down to what kinds of boundary conditions there are. The basal Cambrian sandstone is a very large regional formation, but are there local boundaries which will result in fairly significant pressure buildup? I don't think we know the answer to that with the limited amount of injection that's occurring there so far. I think the Shell Quest experience has been that the pressure buildup that might be associated with injection there has been less than expected. So they've been able to inject the required amount of CO2 with fewer wells than they originally anticipated. So there, it doesn't seem to be a significant issue.
And so an anonymous attendee had sort of the same question that I did. So about the salt buildup in the pipes shown in the second to the last slide, are there efforts to remove these from time to time, or is that really a concern, or is it just something cool to show in the video?
Well, I'm a geophysicist, so I just thought it was cool because you had a camera down a well at high temperature in a supercritical fluid. No, it's whenever you operate wells, I don't have a lot of background in the oil and gas industry, but there are byproducts that affect wells and perforations, asphaltenes in hydrocarbon production, wax buildup, and in this case, it's salt. So in our particular case, the thought is that that salt buildup occurs primarily during periods where the well has been temporarily suspended. So during periods where there's no injection, and the idea is that there is some flow back of brine into the well. It is dried out by the CO2, and because it's super saturated, it precipitates salt. If you looked at the slide which showed injection over time, you can see that it hasn't been a linear line. There have been periods where the plant has been shut down. So that seems to be the issue of, at least we think that's largely the issue of why you get the salt buildup. When you continue to keep the CO2 flowing, you don't get that buildup, or at least that's the thought. However, when you do get the buildup, yes, you will have to do something, some sort of maintenance on those wells. It has been suggested that the circulation of hot fluids is suitable for dissolving those kind of deposits. But given the temperature of the fluids already at that depth, I don't know from an engineering approach how you do that. But yes, if this were a commercial project, something would need to be done to address that salt buildup.
Excellent, thank you. So the next question is from our dean, Dr. Kristen Bates. She said, "What a wonderful talk. I'm curious as to how far the Canadian government is down the path for developing implementation policy or a plan to implement this type of carbon capture strategy. And has there been serious community pushback on these strategies?"
Well, I'm just a lowly scientist within the government hierarchy, so I'm not sure I can answer your question. So the government has certainly supported research into carbon capture and storage. For the last number of years, most of the funding has gone towards the capture side of things. But more recently, the more attention has been given to carbon capture and storage. For the last 10 years, it's kind of been sitting at the side of the road in terms of government interest, I think. But more recently, storage has been included as well in research activities, and they've been expanded. In terms of overall implementation, it's consistent with government policy, but I can't speak to how much effort they're putting into, seeing the rollout of carbon capture and storage. You'll have to get someone else to answer that question.
Okay, so the next question I will ask is from Aaron Rousel. As carbon dioxide is a potentially dangerous gas, it seems odd that we don't hear more about the potential risks of CCS. I appreciate that you touched on things like leakage and induced seismicity. As greenhouse gases are a global issue, can you offer any insight as to how regions of the world with greater levels of geological activity might deal with their emissions? If they were to transport their carbon dioxide to an inactive area, would there be a limit to how much a reservoir could store? So I think we're thinking about tectonic activity. You probably don't want to necessarily inject CO2 in a place that's sort of rifting and fracturing.
Right. Yeah, so right off the bat, there are a number of, if you're talking about site selection in a larger context, you don't want to be in tectonically active areas with active fault zones, primarily because they may damage sealing units in the reservoir itself, but also in a lot of cases, they would represent vertical pathways for the leakage of CO2. So if you're going to put the CO2 in the ground, you want to make sure it's going to stay there. So looking at the map of Canada, there are areas in Western Canada, for instance, that are very tectonically active. And I don't think we would consider those for CO2 storage. If you move to the Western Canada Basin, certainly in southern Saskatchewan, that's about as stable a part of the craton as you're going to find. So, you have to make those kinds of strategic decisions about, just because you have a storage formation doesn't mean you should utilize it. The other thing which we've learned in the past 10 to 15 years is even in tectonically quiet areas, for instance, Oklahoma, if you start to inject fluids, you can induce seismicity and induce seismicity of significant magnitudes. We've seen it in fracking as well. So there are a variety of geological considerations if you're going to consider doing this on the large scale, and areas will have to be considered region by region to come up with a plan of where the best areas are for CO2 storage. And I think we're going to learn some things as we roll these big projects out, if they do occur. I think we will get some surprises over time, which we will adapt to.
Excellent. Thank you very much for that answer. So the next question I'm going to ask is from, again, Paul Bowman. And I think this will play to your strong suits and the theme of this lecture tour. Are there any surface geophysical or other surface geophysical methods that are successful at either detecting or crudely imaging the CO2 plume?
I'm just quickly trying to think other than seismic. Once you get large masses of CO2 in the ground, then you can start to see it with other surface geophysical techniques, for instance, electromagnetics or gravity. And in particular, if you were to have a significant amount of CO2 to leak from the reservoir and get above that critical depth of 800 meters, then the properties of the CO2 change significantly. And surface methods certainly will be sensitive enough to sense that CO2. Of course, synthetic aperture radar measurements, INSAR, interferometry, looking at surface deformation. Again, once you have larger volumes, so things like 1 million tons in the ground, then you can start to see signals at the surface. There's enough sensitivity to actually see the injection-induced signals. So there are other techniques, but for the amount we have in the ground at Aquastor and at the depth of 3.5 kilometers, most of the other methods don't have the sensitivity to see it.
Okay, we have time for just one or two more questions. So I'm going to ask a question from Kathleen Nestor, who asks, when looking for a suitable injection location, are there any preferred properties in the shale cap rock? Are there properties similar to those that would be used in SAGD operations, for example? Probably not the most ideal place to inject CO2, right?
In SAGD operations, do you mean?
Or in cap rocks in general, you'd probably want to avoid injecting into the shale itself.
in the cap rock itself? No, I mean that could be a fracking operation. So yeah, I'm not making light of the question, but generally, no. I think you want easy targets that have significant injectivity, so permeability and capacity for storage, so porosity.
Yeah, and I agree. As sort of in my history of doing sedimentary basin CCS, there was a time, and there still is this time, right, where we're fracking the shale cap rocks and potentially destroying the seal that we need to store the CO2. So it's definitely a play backwards and forwards on that. So I will ask this final question, which is from my co-host, Dr. David Eaton. Don, since you have toured the country with this presentation, have you discerned much variability in how audiences in different areas respond to the deployment of CCS technology?
The simple answer is yes. Some audiences, I would say at some of the smaller universities where they don't have geophysics programs per se, a lot of this is kind of news. they're not that aware of it. Once you get into the Western universities, of course, they're all familiar with it, and they can name some of the existing projects. And I would guess, in general, the debate is more intense because more is known about it from both sides. Those who question whether we should be putting resources into carbon capture and storage or not, versus those who think it needs to be deployed if we're going to reach the goals that we've put in place globally. Yeah, each one's been a little bit different, Dave, but that's about as much a generalization as I can give you. But I would say the one question I've been asked a number of times is the question of diverting resources for research or development of carbon capture and storage, diverting them away from research or deployment of renewables, for instance. But my general answer to that is, that one slide I showed, there's no panacea with one given method. And given the global dependence on hydrocarbons, still, it's not going to happen overnight. So we have to do a number of different things to reach the goals that we've set internationally.
Excellent. Thank you very much for your wonderful presentation tonight. And thank you everyone out there for your questions. It's been a pleasure being with you for tonight's event, and I hope that you'll be able to attend future Gallagher presentations. I will now turn it over to Dr. Stephen Hubbard, the chair of the Department of Geoscience.
Good evening, everybody. It's been great to be here. I really want to thank Don for joining us this evening and sharing some fascinating research. It was a great presentation on a topic of broad interest to our community, as you could clearly see from the engaging question and answer period. And really just overall a great contribution to our Gallagher talk series. To each of you that have attended tonight's lecture, before you leave, I do want to remind you that we have one final talk in our winter Gallagher Colloquium series schedule. Wednesday, March 30th, Dr. Shauna Morrison will join us from the Carnegie Institute to discuss driving curiosity, exploring Martian geology and habitability through mineralogy. Additionally, on Thursday, March 17th, for the Howard Street Robinson Lecture put on by the Geological Association of Canada, Dr. Elizabeth Turner from Laurentian University will be with us to discuss her latest research findings. And the title of her talk is this the oldest known animal fossil? A novel approach to Precambrian Metazoan evolution. And lastly, I'd like to draw your attention to a university theater production titled Formations, which runs on March 28th and 29th. This production is about the unknown histories of female scientists who changed the world. It is a collaboration between Dr. Glenn Dolphin, Tamarat Chair and Senior Instructor in our Geoscience Department, and drama faculty members in arts. If you haven't been receiving our emails about the Gallagher Lecture Series and other events and would like to subscribe, please do so. Please email scialumni@ucalgary.ca. We have shared the links to the aforementioned events and our email address in the chat. Now, we've also shared the link to our faculty's donate page. While we receive our core funding from the provincial government, much of the extra support for our students and researchers or events just like this one are made possible through individual and corporate gifts. Gifts of $10 or $20 even add up quickly and make a real impact. So please do consider the option. Lastly, when you do see our event survey in your inbox, please take a moment to fill it out. Your feedback is important to us, and we do want to hear from you. Again, thank you for coming and enjoy the rest of your evening.